By Eleny Ionel from Stanford University, who's going to talk about thin compactifications and relative fundamental classes.
Okay, thank you. First, I would like to thank the organizers for inviting me. It's always great to be back in Rio, and at IMPA especially. The talk today is based on joint work with Tom Parker. And it's a series of papers. The first two have already appeared, and these are the two I'm going to talk about. And I should say before I start that we benefited, at the beginning of the project, we benefited from discussions with John Morgan and also with John Pardon. So let me start with the motivation. Maybe and results, briefly. I'll state the result. So let's consider the following classical situation. We'll consider some moduli space. Over some parameter space. Okay. So you just need this map to be Fredholm. Okay. Sufficiently differentiable. Okay. And let's consider the compactification. Let me draw a picture. So we've got some parameter space P, and we've got some moduli space. And we consider compactification m bar, pi bar over p, which just means that pi bar is continuous and proper. Okay. So we compactify the moduli space. I don't know how to, we have to add some bad strata perhaps, and some bigger pieces. It's hard to draw, but anyway, that's a picture of the compactification. M bar, and we have this map extends over the compactification in a continuous and proper manner. Okay, so let me also assume, so I'm going to assume the following two things, that this extension, that, when you compactify the moduli space, you add some strata, and let's assume that, let's say that we have transversality strata-wise. Which simply means that this extension pi bar restricted to the strata that I have added, strata, is Fredholm. Okay. And I'm also going to assume that the strata, the boundary strata that I have added, are codimension at least 2. Okay? So this is a classical setup when first invariants were defined. Okay? Then Sart's-Mail theorem will tell us that we have the following properties. The first property is that for generic fiber, so let me just say it this way, the generic fiber, let me denote that m bar p, so it's over a point p here. Oops. Anyway, that's m bar p. The generic fiber, well, is compact, we know because it's by its proper, is compact, but it's a manifold away from codimension 2. That's the first thing. And the second thing, Sart's-Mail will give us something similar for paths. So something similar, we have a, maybe just say it like that, similar condition over, similar condition for the moduli space m gamma over a generic path. I mean, this moduli space will be a manifold with boundary, but again, away from codimension 2 strata. Okay? So that's Sart's-Mail. That's what classically Sart's-Mail will give us. We'll call this condition star. And then, of course, this is good enough to get invariance. Okay. So that's the classical situation. What I want to talk about today is that the very same assumptions, star, actually give us much more. So let me state the result. So this is the theorem. And it will be under the assumption star Okay? We have two properties. The first property is that the generic fiber has a fundamental class. I'll denote it M bar fundamental class in some homology theory. Right, so this is some homology theory. And that become, I'll mention it homology theory. Okay, so that's the first statement. And then the second statement is that there exists a unique extension that associates to any point in the base a fundamental class like that. Maybe I'll call this virtual fundamental class or relative fundamental class. For all points in the parameter space, there exists a unique extension which is consistent, such that it's consistent. Which is to say that i.e. the fundamental class associated at one point is the same as the fundamental class. Let me put it virtual. I may forget to put virtual, but or relative fundamental class. The fundamental class at one point is the same as the fundamental class at another point in the homology of the moduli space over a path for all paths gamma from P to Q. Okay. So that's the theorem I would like to explain today. Okay. Do you have any questions about this? You are curious about what? Oh, yes, thank you, yes. The fundamental class of the compactification is the same as the fundamental class at this point, is the same as the fundamental class at this point in the homology of the moduli space over a path, okay, for any path from P to Q. Okay? So that's, this gives you invariance, if you want, of the invariance. Right? And this tells you that by pairing it with appropriate cohomology classes, you get invariance. All right. So of course, this in particular will give you invariance, but it gives you much more. I'm going to call something that has this property. I'm going to call this a relative fundamental class. Something that has both of these properties. And it's relative because it's relative a family. Okay, so it's obtained from on generic fiber. You'll have a fundamental class, and then you have a family. You extend it over the entire family. So it's relative to the family, the parameter space. Okay. So anyway, so as I said, this gives you invariance. This gives you invariance, the classical invariance. But these have better properties. So let me say that it has better properties. We all know that a homology class is much better than a bunch of numbers. So in particular, what can you do with it? You can push it forward by continuous maps. You can't push forward numbers, but if you've got any continuous map, even to a very singular space, it doesn't have to be smooth. You can push forward these classes and get other classes in the homology of the space and get, then do stuff with it. It has even better properties. So for example, if you have two compactifications, so if we have, maybe I won't write it, maybe I'll say it like that. So, well, okay, maybe I'll write down. So if you have two compactifications of the same space, I'll call them M bar and maybe M bar prime. So these are two compactifications of the same moduli space. They are both, I'm going to assume they both satisfy this condition star, okay, which is stated over there. And I have a map between them, F, which is continuous. So F is continuous. Then you can push forward the fundamental class of one will give you the fundamental class of the other. Okay? And so in particular, again, the invariance you would get from this will be the same. Okay, so it doesn't really matter. I mean, the compactification you use is not so important, but you need it to construct this extension, as I'll show. Other properties that are useful, you can also decompose a fundamental class. So decompose a homology class. Decompose the class. In other words, if you have an open and closed subset of the moduli space, then its complement is also open and closed, and it's a class in homology, right? So a class in homology will decompose as a piece in that open and closed subset. So if X is open and closed, then you have a piece, right, this fundamental class that you have, any homology class that you have, in particular this one, will decompose as a piece coming from the contribution of X in homology and another piece coming from the complement of X, right? Okay. So for example, if you go back to the talk by Chris Wendell, in the case where you have a curve which is super rigid, it has all its multiple covers. The condition that it's super rigid simply implies that the space of covers of that curve, it's both open and closed in the moduli space. And so in particular, it has a well-defined contribution to the invariant or to the fundamental class. Okay? So you can decompose the class. And I should also say that our construction, maybe I'll write it here so I don't start a new blackboard. Our construction is compatible with the classical definitions of Gromov-Witten invariance. So it's compatible with the definition using pseudocycles. It's also compatible with cut-down. Sometimes you define invariance using cut-down moduli spaces. This is compatible with the cut-down moduli spaces. Construction. And it's also compatible with Pardon's definition of the virtual fundamental class using implicit atlases. Okay. Just to mention, this is not to say, so it's compatible, for example, with Pardon's definition in the situation where you've got such a compactification with codimension 2 strata, which also happens to have an implicit atlas. Okay? So again, having a compactification with codimension 2 strata, it may be a stronger condition than Pardon's definition may work more generally. You may have an implicit atlas without having a compactification with codimension 2 strata. But if you happen to have a compactification with codimension 2 strata, which also has an implicit atlas, then the two definitions are the same. Yes?
And his Czech homology equals the fancy H?
Yeah, I'll tell you which homology theory to use. Okay?
It's equal.
It's equal. Yes, it is. Well, okay, yes. It pushes forward. This class that we have pushes forward to his class. Okay? Okay? Other questions? Okay, so that's a brief motivation and a summary of the results. So let me first mention what homology theory we use. Maybe also I should say the homology theory we use, and this result rests on work that was well known in the 70s, algebraic topology that was well known in the 70s, and also used in the 90s. So it's, if you want, classical, but it's not so well known. And it's not easy to find good expositions of these constructions. All right, so which homology theory should we use? Okay. So first of all, I should say that singular homology is hopeless. If you want to use singular homology, a result of this form, you're just absolutely not going to happen. Okay? So it's better to use what's called Czech type homology. We're going to use what are called Czech type homology theory. These sometimes are called type 2 homology theories. So there are several of these and natural maps between them. So there are several of them and natural maps. And I'll present. But what I need to mention before I start is you need to give up something. So for example, if you care about this homology theory being homotopy invariant, these homology theories are not going to be homotopy invariant. Okay? So you have to live with this. But then you gain some wonderful properties. One of them is called relative homeomorphism, and another one is called continuity property, which we're going to use to extend continuously, if you want, over the non-generic points. Okay? So there are several Czech-type homology theories and natural maps between them. So the simplest one is the, is the dual to Czech cohomology. Okay, so this is dual to Czech cohomology. Okay, that's where Pardon's virtual fundamental class lives. So that's, hopefully everybody is familiar with Czech cohomology. Right? I mean, dual to Czech homology. Then there is another homology theory called Czech homology. I've never heard of Czech homology before. How many of you have heard, I mean, before I started this project, how many of you have heard of Czech homology? Okay, some people have heard of Czech homology. So the problem with this Czech homology, one has to be careful, it's not exact over Z. Okay, that's really bad. But it's okay over Q, so it's exact over Q. Okay. Yes? It's not exact, so you don't have, if you don't have the short exact sequence, then it gives you a long exact sequence, which is a bit disturbing. I mean, all right? But there is another theory called Steenrod homology. Oops, Steenrod homology. So this is called Steenrod homology. That remedies this defect. So it's exact over Z, and it satisfies the Allenberg-Steenrod axioms and everything. Plus more. Okay? So it has the usual properties. It's exact over Z. So you get long exact sequences from short exact sequences, and several other properties that are going to be very useful for us. So let me tell you what are these properties. Oh, maybe I should also say that over Q, with Q coefficients, all these theories are the same. So, you know, if you don't care about integer coefficients, these theories are the same. Also, for compact metric spaces, any coefficients, these theories are the same. Okay? So if you want to work with compact metric spaces, then it's the same thing. Yes?
Are any homotopy invariant?
No, they're not homotopy invariant. If you care, they're also equal for compact metric spaces. They're also equal to Borel-Moore homology, which is the homology used in algebraic geometry. Okay? For the fundamental class of a variety. Okay. But they're not homotopy equivalent. They're not homotopy invariant. So that is the, if you want. I mean, I'm not aware of a place where you use homotopy invariance. I mean, it's useful to have homotopy invariance, but I'm not aware of a place where you use it in defining invariance. Yes?
I think when you say this last one satisfies Allenberg-Steenrod axiom, it sounds like it would make it the same as singular homology.
No, it's not. It's like equal to singular homology for simplistic complexes, but it's not. Oh, yes. Sorry. One proviso. The best setting, so again, as I said, it has more properties, right? But the setting, this is not defined for all spaces. So the best setting, it can be defined slightly larger, but let's not worry about that. But the best setting is for locally compact, Hausdorff spaces. Look, all my spaces are going to be Hausdorff, but you need locally compact. And the morphisms, the maps between, have to be continuous and proper. Okay? So you can't push forward in homology unless you have both a continuous and proper map. For example, if it extends to a compactification. Okay? So this is the setup in which you work. Right, the maps from between spaces are X. Okay, so I should have said that. So what are these other properties I was mentioning? So here are the properties, the two properties. So one property, let me call it 1, is that for any a closed subset of X, so X is in this category, right? Any closed subset of such an X, there exists a long exact sequence. So H star of A goes by inclusion into H star of X. Now goes by restriction to an open set, which is a new, it's a new map. Well, it's not really so new, but anyway, it goes by restriction to the homology of the difference. It goes by the boundary map, okay, I'll call it the connecting homomorphism, to the homology of A, the homology -1 of A. Continues, okay? This may look odd, but the reason why this may look odd is this is actually the same as the homology of the pair. These homology theories are what are called single space theories. This is the same as the homology of the pair, X rel A. It's a closed pair. This is because of what's called relative homeomorphism property, which says that if you have a closed pair, the homology of a closed pair depends only on the difference. It really does not depend how this stuff fits into X. Okay, so it could fit horribly. You don't need a color, you don't need any gluing, you don't need anything. You just need, just depends on the difference. Okay, so that's one nice property, which is something very useful here. And a second useful property. I'm not sure why I'm crumbling this chalk so much. I'm sorry. The second property, I'll try maybe to use smaller pieces. The second property is that for any M-oriented, let's do oriented. I don't want to work with twisted coefficients, okay? So oriented, anyway, I could, but it's a bit fishy, okay? So any M-oriented, let's say, d-dimensional manifold, okay? Not necessarily compact, but Hausdorff, okay? Has to be Hausdorff, has a fundamental class. Did I say Steenrod? I should have said Steenrod. But it also works. It doesn't work for Czech, but anyway, Steenrod. This is Steenrod, has a fundamental class M in Steenrod homology. So it's really based on infinite chains. What's called? It's a construction of this on infinite chains. So it's not on finite chains, as you would be expected. So for example, the open ball has a fundamental class. The homology, the d-dimensional, whatever, if it's a d-dimensional ball, the homology of the d-dimensional ball is actually Z, and it has a fundamental class, the generator. Okay? So it's slightly, your intuition may be slightly off a little bit. It's fine for compact, for manifolds. Compact manifolds is the same fundamental class, but it also, you have a fundamental class for open manifolds. Okay? So now the problem, if you want, is that if you want to push it forward, right, you need F proper. So for example, extends to the compactification. So if you want to push forward this class in homology, you need, as I said, continuous proper maps. All my maps are continuous, unless I say otherwise, okay? But you need proper maps as well, okay? All right? So this motivates, so these are two of the properties. It has one more property I will mention in the next section. But for now, these are the two properties that we need to construct, to extend the fundamental class from the interior to the compactification if the boundary is codimension 2. So let me do that. Okay. Yes?
Infinite chains?
Yes.
Still locally finite?
Locally finite but infinite chains. Locally finite but infinite chains, yes. And it's, by the way, this is dual to Alexander Spanier cohomology. I mean, I don't know. Again, I've learned so much algebraic topology that I never knew existed in this project. But these were all classical results, from the 70s, and also it's used in other fields of mathematics, especially as you'll see, it has one more property called continuity, which is very, very useful. So this Czech type theories are very useful for things that you cannot quite control how they fit together. Okay. All right. Okay. So the next section is thin compactifications. So the setup here is that I have M, a d-dimensional manifold, oriented, not necessarily compact, but Hausdorff. Okay, I'm not going to say that. Okay, a compactification. Let's call it M bar of M is thin if the singular locus, which is what you add to compactify, let me draw a picture. So I don't know, we've got some manifold, open maybe, and we compactify it, and I don't really know how to draw this, but I'll try my best. Anyway, we compactify it by adding some, I don't know, again, some bad stuff. Maybe we do some cone here to compactify. Okay, the red stuff, it's the singular locus we need to add to get something compact. So if the singular locus, of course I need this to be closed. Okay, and that's what a compactification would mean, but it's closed and homologically codimension 2. I.e., it's Rod homology. Say if you work in Rod homology, is 0 in all dimensions which are strictly bigger than d minus 2. So homologically, it's codimension 2. It doesn't have any homology beyond d minus 2 dimensions. Okay? So then the little fact or property is that the fundamental class, there exists a unique extension of the fundamental class of a manifold to any thin compactification M bar. And the reason for that is very simple. You have this long exact sequence, okay, and applied for the compactification and the singular locus, and that's your manifold. And so you just get these two groups are isomorphic, right? So you simply get that the homology of your compactification is isomorphic to, in dimension d, which is where the fundamental class lives, of your M, right, by the long exact sequence. So you've got here the fundamental class of your manifold, and this is your M bar. So it's very simple. It's a very simple observation, but it has a unique extension simply because these groups are the same, naturally isomorphic. And in fact, as you notice, really this extension is really, if you want, in some sense, independent of the compactification. These groups are canonically isomorphic regardless what compactification you use. Okay? So in that sense, whatever extension you have to compactification, they would correspond because they both correspond to the homology class of the interior. Right? Okay? And it's really false for singular homology. Okay. This relative homeomorphism is also false for singular homology. Okay. So let me give you an example. Where's my eraser? Excuse me? Yeah, this is Rod. Yes, thank you. Thank you. This is Rod. Yes. This is the Rod homology, yes. Yes, exactly. That's my example. If dimension is at least 2, then it's the one-point compactification, it's thin. Yes, exactly. And that, to some extent, that's how some of these theories are actually defined. The Czech homology is defined, you define it first for compact spaces, which is the best, easiest way to define it, and then you extend it to the locally compact spaces by taking the one-point compactification. And that's one definition of Czech homology. All right, so example. If dimension of M is at least 2, then the one-point compactification is thin. Okay. And it's in some sense the smaller such compactification. Now the problem is most maps you care about don't extend continuously to the one-point compactification. Okay? So the game is to find a compactification which is big enough such that maps you care about, you care in certain maps, right? The maps you care about extend to it, but also small enough such that it's still thin. Okay, so that's usually the game if you want to define invariance. You have to find the compactification so that you have the evaluation map. If you do Gromov-Witten theory, the evaluation map or stabilization map or whatever other map you may care about extends over the compactification, but still the boundary is codimension 2. Yeah, that's the usual game. Okay. All right. Now, of course, I didn't tell you how to define this Rod homology, and it's a pretty, the definition is somewhat involved. So how would you check something is homologically codimension 2? Here is a very useful criteria. For example, a criteria for when the compactification is thin. So if S, which is the singular locus, which is defined to be M minus M bar. So I'm assuming M bar is compact, okay? And I'm assuming S is closed, right? Or in other words, compact. So if this guy, so I'm just writing down what is the condition that it's codimension 2. Okay? So if this S can be covered by countably many, countably many images, let me call them phi alpha of n alpha, where n alpha are manifolds of codimension at least 2, and phi alpha are either, each phi alpha, right, are either continuous and locally injective, or locally Lipschitz, then S is codimension 2, homologically codimension 2, in Rod homology, then S is homologically codimension 2. So that means the compactification is thin. Okay. So that's a very useful criteria. And this is basically most of the examples we know fit in this, into one of these categories. Let me give you one example. So for example, often moduli spaces are stratified by manifolds. Right? So the first example, if the the compactification is stratified by manifolds, well, then you are in case A. A applies. Well, if this manifold has codimension 2. Okay. A applies. Or another case, if these phi alpha are smooth, or C1, you just need them to be C1, then they are, of course, locally Lipschitz. So B applies. Okay. So that would be the case, for example, for pseudocycles. Okay. So these are two criteria that you can play with them. Okay. All my manifolds are, compact, and these ones are, all my manifolds, these don't have to be compact, right? They're manifolds, they're all Hausdorff, and let's say sigma compact, okay, or metrizable, whichever one. Questions? All right. Okay. Let me just say it this way. M bar minus M is stratified by codimension two manifolds. Okay. All right. So then I'm not going to go into this, but there is a parallel discussion about thin cobordisms. Yes? Well, you need, so what would mean, right, exactly. What would mean locally Lipschitz would mean that this is metrizable, and you can find a metric so that it's locally Lipschitz. Okay, ultimately, the point is that, its homological dimension doesn't depend on the metric. But in order to prove that the image of something decreases dimension, you need that something to satisfy some properties, either continuity and locally injective, or otherwise locally Lipschitz. So there exists a metric on the domain, and there exists a metric on the target. You break it into pieces so that it's Lipschitz. Okay. I mean, otherwise it could behave really badly. Okay. There are examples where dimension increases under continuous maps. Well, we all we all have examples of such, curves, plane filling curves and stuff like that, right, where the dimension of the image is bigger than the dimension of the domain. Okay? So you want to rule that out, and that either this one or this one will rule that bad behavior out. Okay? Other questions? So the thin cobordisms, the only property we care about, so again, the picture is the same. You are over a path. You are going from P to Q, and you've got some moduli space over this path, and then you compactify it. You have some cobordism, I should say. So we don't have moduli space. We have some cobordism, and then you compactify by adding some stuff on the boundary and adding some stuff in interior. And that's your compactification, M gamma. And the only thing, the main property that you get is that the fundamental class at the beginning is the same as the fundamental class at the end in the Rod homology of this compactified cobordism, if it's thin, okay, d-dimensional, as before, right? So gamma is a path from P to Q. I'm not going to write it down. Okay, so that's the main property that you get. You have this relation before you compactify, and then you compactify, then show this relation continues to hold. Okay, all right. Okay, so that's the first part about thin compactification. Now this discussion extends easily to families. I have until 4:30, correct? Yes, thank you. Okay, so this extends easily to families. So let's extend this to families. I think I'm on number 3. Families. Okay. So in order to extend this to families, it's almost like here, but I have maybe a bigger dimensional family. In order to extend this to families, we're going to use another property. We're going to take our class in Steenrod, push it to Czech, and then use the continuity property of Czech. So for families, we're going to extend by pushing first forward to Czech homology. Either Czech homology, or if you prefer, you can push it all the way down to the dual of Czech homology. And use their continuity property. So Czech homology has the following continuity property, that if you have an inverse system, so if you have X alpha, an inverse system, I'm dropping the maps, okay, but you can do it with maps. Inverse system inverse system of compact Hausdorff. I keep adding Hausdorff, but all my spaces are Hausdorff, but I just want to make sure I keep adding it. Compact Hausdorff, then the homology of the limit is the limit of the homologies. So the homology, Czech homology of the limit is naturally isomorphic. I'm going to go over a bit. To the limit of the homology theories. So that's a very useful property. And again, it's false for singular. Okay. So if you want, for example, we can at this point, if you don't want to push to check, I mean, we can work with Q coefficients. The reason why I'm not doing this in steroid homology, maybe I shouldn't get too technical here, but steroid homology has a continuity property where this is not always an isomorphism. There is a derived Lim1 term, so which vanishes over Q, or in certain cases, but it's not worth the trouble. If you can just push it forward in check, and it has this version of check of continuity. Okay, so with this continuity property, now you can just take the fundamental class that we have for the generic fiber and then extend it continuously over every other fiber, okay, using this property. Okay. So let me give you a definition. So I'm going to assume pi from M to P is a Fredholm family, Fredholm map, right? And let's assume it's relatively orientable and sufficiently differentiable, okay? Actually, I don't need to assume it's sufficiently differentiable, sorry. Okay, I just need to know it's relatively orientable, okay? A thinly compactified a thinly compactified, a thin compactification of this family, let me call it like that, a thin compactification of this family. So I'm regarding this as a family of moduli spaces, a family of spaces parametrized by this parameter. Okay. So a thin compactification of this family is, is a proper continuous extension pi bar. And just so that we don't have any trouble, I'm going to assume this guy is metrizable. Okay? Compact and metrizable means all these theories are the same. So, such that M bar is metrizable. Most of the moduli spaces we care about are metrizable anyway, so it's not too much assumption. And the generic fiber, in other words, there is a second Baire category set. The generic fiber, M bar P, is a thin compactification of a manifold. And B, the generic path over generic path, M bar gamma, is a thin cobordism. So it's just a situation, these are just the assumptions I had at the beginning of the talk. The only extra assumption I'm putting here is that M bar is metrizable. Okay? This compactification is metrizable. Okay? Pi bar, sorry. I'm extending it, right? So I have an extension. Okay? So that's what I would mean by a thinly compactified family. Okay? And again, the main example of such a thinly compactified families is when M bar minus M is stratified by manifolds, by codimension 2 manifolds, or more generally, covered by such, as in the criteria over there. Right? As in the criteria over there. Okay. Those are the main examples of thinly compactified families. Okay. So once you know that the generic fiber is a thin compactification and also the generic path is a thin cobordism, then you get our result. Let me state it again. Okay. So here is the theorem again. A thinly compactified family has a unique relative fundamental class, which is to say that you've got an association. Maybe I don't know, I have to repeat, but to each point in the base, you've got a fundamental class or virtual fundamental class associated to that point. It doesn't matter what homology theory I put here because I'm doing compact metric, so they're all the same. There's a beautiful theorem by Milner that all those theories we had for compact metrics, they all agree. There is a unique theory that satisfies these extra properties. So you have this property. You have such an association for all P, satisfying the two conditions. For generic fiber, is for the fibers there is the actual fundamental class, right? Extended to the thin compactification uniqueness we discussed, and also it's consistent in paths, right? Such that satisfies the regularity axiom that says this virtual fundamental class is the actual fundamental class if for generic P. Those, right? The generic fiber was a thin compactification, so we saw those had a unique fundamental class. And then the second property is consistency, that the fundamental class, the relative fundamental class, is the same in the Czech homology, say, of M bar gamma, or Steenrod, or whatever, whichever one you want, Czech homology in this for all gamma paths from P to Q. Okay. So that's the main result. Yes? Oh, yeah. Sorry. Yes, yes. Thank you. It's always in the homology of the fiber. Okay. So it's not in the homology of the total space. It's in the homology of the fiber. Okay. I forgot to give you examples of thin families. I rushed to give you the theorem. But what will be? Actually, no. That's where they were in my notes, so I haven't rushed. Let me just say, so there is not much to say about the proof. It's basically straightforward. You've got this P, and you've got this moduli space, and you've got this extension that is pretty bad, right? You've got this compactification with codimension 2 strata. But the point is that for generic point, right, if you look at the over generic point, you know that the fiber, it's a thin manifold, so that means it has a fundamental class, and this fundamental class extends uniquely over the compactification. So you use the first properties to extend the fundamental class over the compactification, and then you use and you know this is consistent in generic paths by the second assumption, and then you use the continuity property to extend it everywhere. Okay. So let me give you some examples of thin families. So a simple example of thin family is take an elliptic fibration with a multiple fiber. Okay. So this is an elliptic fibration. First simple example, elliptic fibration with a multiple fiber. That's a picture of the multiple fiber. then this is a thin family. It has a relative fundamental class. The relative fundamental class is the fundamental class of each regular fiber. But then here it's m. If it's multiple, it's m times the fundamental class of this fiber. Okay, so that's why it depends on the family. Okay. Okay. Another example. So that's example 1. Example 2. The blow up. So let me try to draw the blow up like that. So this is a picture of the blow up. Okay. This is also a thinly compactified family. Okay. The generic fiber is thin. I mean, it's a point. But this fiber is not. And the relative fundamental class extends over this. Even though this fiber is smooth, the relative fundamental class is in 0 dimension. This is an index 0 problem. And so it extends as a point, okay, in the homology of the exceptional divisor. Okay, these are too simple. So more importantly, the examples we care about, the Uhlenbeck compactification of the moduli space over the space of metrics, so in gauge theory, in Donaldson theory, over the space of metrics, is actually thin. Even though when you construct I don't expect you to know the Uhlenbeck compactification, but when you add in the boundary, you add something which is codimension 8, and it's pretty singular, but still this is a thin compactification because it's codimension 8. And then it's a thin compactification, so it has a relative fundamental class, and then you get invariance from it. Okay? So that's, its classical result. And actually, to some extent, there is an old paper by Donaldson and Kronheimer where they actually use even Rod homology, and they basically make this. If you read the argument, they basically make the same kind of argument that you've got a fundamental class in the right homology theory. There's also an older paper of Hofer, where Rod homology appears. And then the other example that maybe we care most about is that if you look at stable map compactification, if you look at Gromov-Witten theory, right? So this is Donaldson theory. This is in Donaldson theory. If you look in Gromov-Witten theory, you need some assumptions. So if all domains are stable, then the stable map compactification is a thin family. So you, in particular, have this relative fundamental class. You can relax. If you don't have all domains are stable, you can impose some topological conditions. So if you want the stable map compactification to be thin, you can say, or C1, the homology class on A is at least 2 on all unstable spheres, unstable J holomorphic spheres. I mean, basically, whatever you need to get boundary codimension 2, okay, then it also implies that the stable map compactification is thin because you replace, right, this takes care of multiple covers, right? So I should have said, if all domains are stable, I have to tell you the stable map compactification is thin over what parameter space, right? So the parameter space over domain-dependent perturbations, for example, Rantian perturbations, I'll just say it like that, over the space of almost complex structures together with domain-dependent perturbations. Right? And then this condition allows you to cover the boundary strata, right, the multiple covers, the bad multiple covers that are maybe unstable, allow you to cover by something which is still codimension 2. Okay? If you want semi-positive, just for experts. If you want to do this for semi-positive, which means C1 is big or equal to 0 on all such spheres, or otherwise very negative, you're not going to get stable map compactification being thin, but you get a smaller compactification being thin that only sees the image of the curves, but not the maps. Okay? So there is a smaller compactification which is thin. And then, you know, the game for Gromov-Witten theory is to get yourself to a situation where all domains are stable or C1 is very large, prove properties there, and then push them forward. So let me just say, before, just to end, what are these properties? So what are the main properties of this theory? Not of this theory, but of this relative fundamental classes. So I think I'm at number 4, maybe. And maybe since I have less than 2 minutes and a half, the main property is that the codimension 2 stuff does not matter. And so in particular, you know, you don't need to do any gluing if you want to construct a virtual fundamental class. You don't need to find any color theorem or anything like that, as long as you know boundary is codimension 2. If you have some boundary which is codimension 1, you'll have to do gluing along boundary which is codimension 1, but only along the codimension 1. Again, codimension 2 doesn't matter, right? So you just do one gluing. Along codimension 1 things, if you had any codimension 1 things. Of course, if you have stuff which is higher dimensional, then you're out of luck, right? This won't work. You know, and then as I said, if you have 2 different compactifications, you have good formulas that, well, if you have 2 different compactifications which are both thin, then the fundamental class pushes forward, and a continuous map between them, then the fundamental class pushes forward. So the compactification doesn't matter as long as it is codimension 2. So for example, for some applications, you may want different maps, right? So for Gromov-Witten theory, you certainly care about evaluation and maybe stabilization map being continuous, or extending continuously over the compactification. See, for this reduced compactification, the stabilization map will not extend continuously over the domain. Right? This reduced compactification, only the evaluation map extends continuously. But maybe there are some other maps you care about that you want to extend continuously. The compactification, you may modify the compactification. As long as it's thin, then the fundamental class, the virtual fundamental class will be the same, will push forward. Okay? So, and so let me say it like that. So if, well, okay, I guess I have, maybe I'll just say, maybe I'll just wrap it up. So the compactification used doesn't matter. As I said before, it's consistent, it's compatible with Pardon's construction of the virtual fundamental cycle if the 2 things have a fundamental cycle. So if you have a compactification which is thin, and also that compactification has an implicit atlas on it, then the 2 fundamental classes are equal. Okay. And then also it's compatible with the pseudo-cycle definition as well as the definition using the cut-down moduli spaces. If you have such a thin compactification and a map to a smooth manifold, say that restricts to each strata is a smooth map, then the image is a pseudo-cycle, and if you push forward this relative fundamental class, then you get the same as a pseudo-cycle class. And furthermore, right, so you have an M bar, and then you've got some map to N, which is a manifold. For example, under the evaluation map, in Gromov-Witten theory, right, this would be the evaluation map. If you go into a manifold, then the image is a pseudo-cycle, and the pseudo-cycle class agrees with the push forward of this relative fundamental class. So you get F push forward of M bar P is the pseudo-cycle class, Fp. So that's the compatibility with the pseudo-cycle class. And then if you have here a submanifold Y, right, and this F, let's say F restricted to each stratum, it's transverse to Y. Right? So F is transverse to Y, which is to say restricted to each stratum is transverse to Y. Then the inverse image, F bar, yeah, Fp, the inverse image of y, carries itself a fundamental, it's a thin compactification, and it carries a virtual fundamental cycle, and this fundamental cycle is the fundamental cycle of the original moduli space, of the original fiber, cap with a Tom class of y. Right, so this Tom class of y is an element in Czech homology of the manifold, ambient manifold n relative n minus y. Okay. So that's you know, that's the compatibility with Cadal moduli space. Maybe I'll stop here because I ran out of time.